Hello everyone, welcome to lecture 12. Last time we started the discussion on nodal analysis, and this week we are going to continue to finish nodal analysis and start mesh analysis. So this is our agenda for this week. So I'd like to start by a quick reminder that here we are not introducing any new physics, that all the physics of the circuits we've already covered in the form of KVL and KCL and element relationships. And what we're after here is to come up with a more systematic way of writing the circuit equations so that one can more easily deal with larger circuits and eventually program this into a computer code and make things more automatic. But so these are important methods that we have to learn, but we definitely don't want to rely on them for everything. And so frequently we would still be using our KVLs and KCLs depending on the type of problem we are dealing with quite directly. But anyway, yeah, so nodal analysis. Let's start with a quick reminder that if you're considering an element in a circuit like this, if you have something like this that has two sides and is possibly connected to a few other things on either side. Well, so there is two nodes on the two sides, and you would have an element voltage and an element current. Nothing new here. And now we are explicitly talking about the node voltages on either side. Let me create more space here. So let's call this capital V1. So this would be the voltage of this node, and this other one capital V2. This would be the voltage of that node. And basically we said that we are going to have a reference node somewhere in the circuit, and this could be any node in the circuit. And typically it's convenient to assume that the node voltage at the reference node is 0. So you have some reference node somewhere, and here you have the rest of the circuit. So this reference node, you would typically attribute a 0 voltage to it. And that just makes things simpler, because a node voltage, so the voltage for a given node, is its voltage difference with respect to the reference. So it's convenient not to have to add a constant to all node voltages. And that's why it's convenient to choose a reference with 0 volts. So what you have to now recall is that essentially we said when you write your node voltages, or the relationship between your node voltages and element voltages, so in this case the fact that this little v, the element voltage, is the difference between V1 and V2, and pay attention to the polarity just because of the way I've chosen to define V and V1 and V2. By doing this, you are essentially implying your KVL. Recall that we talked about this last time, but also at the very beginning of the course, that essentially KVL is a manifestation of the fact that node voltages are well-defined quantities. And so if you think about this loop going from the reference to V1 to node 1, and then to node 2 and coming back to the reference, so if you go like this and write your KVL, basically you are saying you go up by V1. So let's write that KVL. You go up by V1, and it's just my convention. Recall that when I go up, I add a minus. Then go down by V, then go down by V2. So and so that leads to V equals V1 minus V2. So I'll put this in parentheses just to remind ourselves that when we talk about this kind of relationship between an element voltage and the two node voltages on either side, that's really an implementation of KVL. And so that's why when we wrote our nodal analysis equations last time, that we saw that the that's why when we wrote the circuit equations last time and replaced things in terms of node voltages, we saw that the KVL equations became trivial because they were automatically taken care of by the fact that you're writing things in terms of node voltages. So nothing special or strange there. Okay? All right. So let's now move on and try to see this in practice. And so we did an example, a relatively small example last time. And so I want to look at another example now. But before doing that, let's just remind ourselves, maybe more formally, of the steps we need to take to do nodal analysis. So nodal analysis. First of all, we have to define a reference node. And this could be any node in the circuit. Typically, we choose a node. Maybe it's human nature. We are used to liking if the reference node is one of the nodes at the bottom of the circuit, the way it's drawn on the paper. But there is nothing special about that. So it can be anywhere in the circuit. And it's convenient, again, to assign it a 0-volt value. So for convenience, unless for whatever reason you have to do otherwise, but for convenience, give it a node voltage of 0. So that's that. The next step, well, our KVLs are, like we said, automatically taken care of. So we are left with writing the KCLs. So we want to write the KCL equations. And recall that if you have a number of nodes in the circuit, so let's say if you have n nodes, you have n minus 1 independent KCLs, because the last one would be just a combination of the other KCL equations. So in this case, write KCLs for all but the reference node, because the one for the reference node would end up being redundant, or basically one of your KCLs would be redundant. So write KCLs for all but the reference node. So for all nodes except the reference node. Once you have done that, now KCLs are essentially equations that relate currents. What we want to do is to write those currents in terms of node voltages. So, and that comes from primarily your element relationships. So let's say Ohm's law for resistors. So or in your KCLs, replace currents in terms of node voltages. And this is done using element relationships. there you have it. Basically, these now should give you enough equations to solve for the node voltages. Now, there is something special to think about and remember, maybe, and we'll see this in an example that we'll just talk about now. If you want to replace a current in terms of node voltages, think about, well, with resistors, it would be easy because the current is simply the voltage across the resistor divided by its resistance. So the relationship is straightforward. But what if you had an element whose voltage is defined in the circuit? So a voltage source. It could be a dependent voltage source or an independent voltage source. As we've talked about this before, there is no the current in a voltage source can in principle be anything. In practice, of course, there are limitations, but in theory, it can be anything. And it's not a direct function of its voltage. It will be imposed by the circuit, by the overall circuit topology and all the elements. So you can't really replace its current in terms of its voltage. And so you might be disturbed by this because then you have this current that's going to linger on in these equations. But there's nothing to worry about because the voltage source gives you an additional relationship between node voltages. So you will have an extra unknown, but then you will also have an extra equation. So anyway, it's better to see this in practice. So we'll, maybe I'll put a small note here so that we don't, that we have it complete, but we'll see it in more detail. So if there are branches that have voltage sources, although their current would not be directly related to their voltages, there is no particular problem since those voltage sources will give us additional equations relating node voltages. And again, this would be the case regardless of whether the voltage source is an independent source or a dependent source. And in particular, when you deal with this scenario in nodal analysis, this is called the modified nodal analysis method. Okay, but it's really just nodal analysis explicitly dealing with the currents in these voltage sources. Anyway, let's do an example, and I hope that will help clarify this a lot better. So, example. And I'll draw an example here with just some parameters. We don't necessarily need to worry about numbers for this. I just want to see the patterns that emerge out of writing nodal analysis for this. Okay, so consider the circuit, and basically we want to solve this circuit using nodal analysis, which means first write nodal analysis, find the node voltages, and then from there on you can you can use the node voltages to find all the element voltages and currents and powers, and so have a complete solution of the circuit. So write the nodal analysis equations. For the circuit. Let's give these names: R1, R2, R3, R4, R5, R6, R7, and so that's a voltage source there. This is a current source here, independent, and then here we have a voltage source that's dependent on something else, and in this case let's call this I4, and so this voltage source would be, let's say, alpha times I4. Alpha would be the parameter that defines the control ratio here. So this is a voltage source, but its voltage with the polarity that's indicated is alpha times the current of some other branch. So there's a current controlled voltage source, and down here we have a current source. Let's say also this is a current source that's controlled by the same current I4. So let's call this maybe beta I4. So in this case this is a current controlled current source. Okay, so we want to write the nodal analysis equations for this, and so first step, we have to define a reference, and it can be anywhere in the circuit. Let's say this node down here at the bottom left. So let's call this reference and 0 volts. And now let's go around and see what other nodes we have. So we have one node here, 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 and one node here. And so each of these would have a distinct node voltage, and so let's give them names. Let's say capital V1, V2, V3, V4, V5, V6, and V7. So it's a relatively big problem, and I'm just using this example to show a big circuit. We saw a much simpler circuit last time, so I don't want to do another simple one here. Okay, so well, if we now accept the fact that, again, by choosing to work with these well-defined node voltages, we have already implemented our KVLs like we saw last time. We are not going to need to write them explicitly. They are taken care of automatically. And so we are left with KCLs. And so let's start doing that and see how far we get. So to write KCLs, we need currents, right? And so now we have to define currents for each element in each branch. So let's call this I1. Let's call this I1. And so this would be its element voltage V1. Let's say this is I2. Maybe I'll choose a different, I'll use a different color for these. So let's call this I1, element voltage V1, I2, element voltage V2, I3, element voltage V3, I4 we have already indicated. Let's call this element voltage V4, and I5, element voltage V5, I6, element voltage V6, and I7, element voltage V7. Okay, what else? Are we done? Well, let's see. So you start writing your KCLs at each node. So let's say the first node, V1. Yeah, you have a KCL that says minus I1 minus I2 equals 0. And so you have both. But when you get to node V2, you have a KCL that says I2 minus I3. And then there is another current here that we have to take into account. So let's call that maybe we have I8 is still available. So let's call that I8. And then similarly, when you get to, for instance, node 3, there is this other current. Notice this current is not alpha I4. This is the current of this voltage source. The voltage source itself is controlled by another current source. By another current, I4. But it has a different current, and so let's call this I9. And what else? Now, the other two sources we have are current sources in this case, so their current is pretty well defined. One of them is IS here, and the other one is beta times I4. So we don't need to define any additional current parameters. So basically we have all these variables, all these unknowns, the node voltages V1 through V7, and then those are what we want to obtain eventually. But then as intermediate variables, we've defined things for the elements. And of course, we have to also keep in mind that the current sources do have voltages, like we've talked about before many times. A current source can have any voltage as imposed by the overall solution of the circuit. And so in this case, maybe just for completeness of the element variables, it would be useful to just give these some names. So maybe let's call this V8 and this one V9. And by the way, I could have done the other way too, the polarity of V8 or V9. It didn't have to be this way. It's just my choice. All right, so I have all these blue variables that are really element variables. And these are intermediate in that if I want to write my KCLs, I'll write them in terms of these little currents and then replace in terms of node voltages. So if I start by my first KCL, so KCL at node 1, let's call it KCL 1, is simply minus I1 minus I2 equals 0. And I can continue writing this for all the other nodes. But what we would also like to do is that eventually we are going to replace these with node voltages, or in terms of node voltages. But before that, let's continue writing all the KCLs, and then we'll replace all of them. So KCL2 then is I2 minus I3 minus I8 equals 0. KCL3 is I1 minus I5 minus I9 equals 0. KCL4 is I have I9 minus plus I8 minus I4 minus I6 equals 0. KCL 5 I3 plus I4 plus the current going to node V5, and in this case there is the current controlled current source that has a current of beta I4 equal 0. KCL 6, you have this current source IS going in plus I6 minus I7 equals 0. You have I7 minus beta I4 equals 0. Okay, so we have all the KCLs now. And so next we are going to write these currents in terms of node voltages. And so for instance, for I1, let's take a look. I1 by Ohm's law is simply little v1 divided by R1. And little v1 is the difference between big V1 and big V3, those node voltages, right? So just as an example, I1 is V1 over R1, which is then this. And you can do this for all the other currents through the resistors, right? But when it comes to the currents in the voltage sources, in this case I8 and I9, you can't do this. There isn't a direct relationship. So you have to just keep them as they are. The end result is that although you have 7 KCLs here and 7 node voltages, you will end up with these two extra unknowns, I8 and I9. So the question is how to deal with them. If you have 7 node voltages that are unknown and 2 currents that are unknown, that's 9 unknowns, but you have 7 KCLs, 7 independent KCLs. So you need 2 more equations. Where do those come from? So take a moment and think about that on your own. Okay, so let's see. What else is there in the circuit that we haven't implemented? So first of all, I'm sorry, this was I1. And we'll say similarly for I2 and so on. Don't want to repeat all that. Or write all the Ohm's law. You're familiar with that. So what else do we have here? The only extra pieces of information come from the 2 voltage sources that created the difficulty to begin with. One is Vs. Vs is the voltage difference between the 2 sides of this voltage source. Well, that's just the difference between the 2 node voltages on either side. So additional pieces of information. One is the fact that the difference between node voltage V2 and V4 is simply the voltage of that voltage source, Vs, which is a known of the problem. Vs is just a parameter. So V2 minus V4 is simply Vs. That's actually an equation. So that's one of the missing equations. The other piece is for the other voltage source. In this case, it's a current-controlled voltage source, but it's effectively in the circuit like a voltage source. And in that case, that's the difference between V3 and V4. V3 minus V4 is the voltage of this dependent voltage source, which happens to be alpha I4. So these are things that came from the voltage sources. And that could be an independent or dependent voltage source. Okay? So that's two extra equations. And remember that I4 itself in this case was the current through resistor R4. And that can, using Ohm's law, be related to the node voltages V4 and V5. So no difficulty there. And so now we have to put everything together and basically input our node voltages into the KCL equations. Okay, so see if you can do that on your own. All right, let's do it together. So equation 1, KCL 1. So I1, as we've written here, is V1 minus V3 over R1. And so we just replace that. And then I2 is V1 minus V2 over R2. So the second equation has I2, which is again V1 minus V2, that little V2, over I2. And then it has minus I3. And I3 in this case is little V3 over R3. But little V3 itself is big V2 minus big V5. So V2 minus V5 divided by R3 minus I8. Now I8, as we just talked about it, is not something that you can relate directly to node voltages V2 and V4 because it's the current of a voltage source. So just keep it as it is, minus I8 equals 0. Next KCL, I1, which we have from before, V1 minus V3 by R1, minus I5. Now I5 is little V5 divided by R5. And little V5 is V3 minus the reference voltage, which is 0. So V3, capital V3, divided by R5. So I1, which is V1 minus V2, minus V3 by R1, minus V3 minus 0 by R5. Okay, minus I9. And I9 again is something that we have to keep, as we just discussed. So they're basically just replacing things into the KCLs. And then KCL4, we have I8 and I9, which again we have to keep as they are. And then we have minus I4 minus I6. Okay, so I9 plus I8 minus I4. And I4 is simply little v4 by R4, which is big V4 minus big V5. So by R4. And then minus I6, which is big V4 minus big V6 by R6. Then the next equation, we have I3, which is V2 minus V5 by R3. I4, which is V4 minus V5 by R4. And beta I4, which is beta times V4 minus V5 by R4. So V2 minus V5 by R3 plus V4 minus V5 by R4, and that's 1 times 1 plus beta times that. Then we have the next KCL, which is I6 minus I7 plus IS, and IS is the source current, so that would be a parameter of the problem. So we'll just write things as they are. IS, the parameter, plus I6, which is V4 minus V6 divided by R6. Minus I7, which is V6 minus V7 by R7. And finally, the last equation, I7, which we just said is V6 minus V7 by R7. Minus beta I4, which is V4 minus V5 by R4. Equals 0. So this is basically our KCLs with the currents written in terms of node voltages to the extent possible. And the reason I say that is because recall that the currents I8 and I9 stayed as they were. We couldn't do anything about them. So here we are looking at 7 equations. By the way, please verify these equations to make sure I haven't made a mistake, as I'm doing them here in real time. So verify this. But essentially our 7 KCLs, and we have 7 unknown node voltages, but then 2 unknown currents also. And so we need the additional 2 pieces of information that we talked about up there. V2 minus V4 is Vs. So these are KCLs all the way down to here. And then additional info was V2 minus V4 equals Vs. Again, Vs being the source voltage up there. And then V3 minus V4 being alpha I4. Now alpha I4, I4 itself, of course we can write in terms of node voltages. And that's V4 minus V5 by R4. So this is additional info that we had. And this is due to the voltage sources. So there you go. Now you have 9 equations and 9 unknowns. Now you might say, well, this was already quite an elaborate process, so how does this nodal analysis make things simpler and more systematic? Well, the answer is now we are going to try to see some patterns here. But we should ultimately keep in mind that if you have a big circuit, you are going to have a large number of equations, so there's no way of getting around that. The trick here is that we are trying to be more systematic in writing them, and also having less equations than if you were to keep all the element voltages and all the element currents explicitly in. Now, by recognizing patterns, here's what I mean. Once you get enough practice, you can essentially start writing the KCLs in one step using the node voltages. So consider KCL 1. If you look at the figure, the way I've defined my currents, I1 is leaving and I2 is leaving, and my convention is to include a negative sign for that. So in this case, basically I have minus the current going through the resistor 1. And I could have directly written that current with enough experience in terms of the node voltage differences. So looking at the resistor, I'd see that the way I have defined current I1 is going from node 1 to node 3. And so my Ohm's law would be V1 minus V3 divided by R1 to give me I1. And so I could have written that directly in my KCL1 rather than writing it in terms of I1 and then replacing. So this is something that comes with practice. Okay, and so on for all the other currents. Now, if we look at these equations, we have the system of equations. It has all the unknowns and enough equations for them. And our next task would be to basically do a little bit of algebra to simplify and organize and arrange things, right? And that's really it. So now let's see if we can do that and arrange things. So the first equation, I have V1, V2, and V3. And let's see how I can combine things. And there's, of course, the question of whether you should bring things to the other side to get rid of the negative sign. Later on, we'll talk about how to write these equations, essentially by inspection, much more directly. But here, let's just see what kind of, what we can see from experience that works. So here I have V1 by 1 over R1 and 1 over R2, both with negative sign. So let's take everything and multiply by -1 to get rid of that minus sign, okay? So then I'd have 1 over R1 plus 1 over R2 multiplying V1, and then I would have minus 1 over R2 multiplying V2, and I'd have minus 1 over R1 multiplying V3. So now basically simplifying the equations. So 1 over R1 plus 1 over R2 times V1 okay, then I have minus 1 over R2 times V2 and then similarly I have minus 1 over R1 times V3. For my second equation, I can do the same thing. And so I'd have 1 over R2 times V1, and then minus 1 over R2 plus 1 over R3 times V2, and so on. So let's do that. Sorry, 1 over R2 times V1. Minus 1 over R2 plus 1 over R3 over V2. Plus 1 over R3 times V5. Minus I8. Okay. Next one, V1 over R1. And then I have minus 1 over R1 plus 1 over R5 times V3. Minus I9. And basically you can just continue writing this for all the equations, simplifying like this. And now if you look at this, this is becoming a lot more compact and sort of something that really resembles a system of linear equations. In this case, 9 linear equations and 9 unknowns. So a total of 9 equations and 9 unknowns. So please complete on your own. Complete the rest on your own. And also, of course, verify that what I've done so far is correct. And so you see that, yeah, these are my unknowns: V1, V2, V3, V4, which I haven't seen in these equations yet, but it's somewhere down there, V5, I8, I9. So all of these are the unknowns. And so basically, ultimately, you have a system of all these equations. And this becomes something very easy to solve. In fact, you can just write the whole thing in the form of a matrix, multiplying a vector of unknowns. And on the other side, you would have a vector of knowns, and that will come from the parameters like the IS and VS in this case, the sources that set the circuit into motion. And that's it. You can program this very easily into a calculator, or use any programming language like MATLAB to solve this system. So what's perhaps useful is try to now see some of the patterns that emerge here. And my intention is not to emphasize patterns and pattern recognition, but it's important to see this, because later on we'll talk more about how to write this directly without having to go through all the steps explicitly. And so look at what you see here. Look at the first equation. We have the voltage of node V1, and it's whatever is multiplying it is 1 over R1 plus 1 over R2. Now, if you look at the circuit, it's interesting that node 1 is what R1 and R2 connect to. So that's something interesting to note. So in equation 1, which was KCL for node 1, the coefficient of V1 ended up being the sum of the inverse of the resistances that are connecting to node 1. How about the coefficient for V2? It ended up being minus 1 over R2. Incidentally, R2 is what connects node 2 to node 1. And for V3, the coefficient is minus 1 over R1. And incidentally, R1 is the resistance that connects V1 to V3, or node 3 and 1. Now, these could be a coincidence, but they're actually not. If you look at at the second KCL, now it's interesting because for node 2, for V2, which is for the node for which this KCL is written, you have 1 over R2 plus 1 over R3. And that's, if you look at node 2, the two resistances that connect to it. And if you look at the third equation, you have V3. And V3, the coefficient for V3 is 1 over R1 plus 1 over R5. If you look at node 3, R1 and R5 are the two resistances that connect to it. And so there's these patterns. And we'll talk about this more, but I wanted to bring it to your attention. And in fact, to create consistency for these patterns, you see how in the first equation for V1 I have 1 over R1 plus 1 over R2, but for the second equation I have, for V2 I have minus 1 over R2 plus 1 over R3. So it's actually better if we multiply the second equation by minus 1 to make things consistent that way. Now the coefficient that I have for V2 in the second equation is following exactly the same pattern that I have for the coefficient of V1 in the first equation. And in the same spirit, I'll also multiply the third equation by minus 1, so that the coefficient of V3 in the third equation is following the same pattern as the coefficient of V1 in the first equation and the coefficient of V2 in the second equation, and so on. And so you will see similar patterns in all the other equations too. But again, what I want to emphasize is that you should not rely on memorizing these patterns, but be really able to go through all these steps of nodal analysis, starting from your KCLs and then replacing with node voltages, bringing in any additional information, and then simplifying things into a compact system of equations. But so this is basically it. This is nodal analysis in a very general form. And like I said, again, when you have this case of these voltage sources that introduce the currents, in this case I8 and I9, which perhaps were difficult to deal with at first sight, then this gives you the additional information that the voltage sources themselves bring, because they impose a relationship or a difference between the voltages of the two nodes on their sides. And these additional pieces of information complete your system of equations. And this is called modified nodal analysis, that contains all this, all these variables, including those unknown currents of the voltage sources. So this is pretty general, and the example that we did here is a circuit that has all these different varieties in it. Okay, so when you work on your assignment, basically for now, very strongly urge you to start by writing your KCLs in this form and then replacing things in terms of node voltages as much as you can and proceeding, rather than trying to recognize the patterns and input them from the beginning. Okay, because this is really how you need to practice to develop the insight and skill, and then gradually you will be able to do it faster. So this is the essence of nodal analysis. Now the last thing I want to bring to your attention is that, as discussed, you can write this in the form of a matrix equation. And for that, what we are saying is that we are acknowledging that we have unknowns. So putting this into matrix form, basically. Putting this into matrix form. We are acknowledging that we have these unknowns, V1, V2, V3, V4, V5, V6, V7. And in this case, there was also the two currents, I8 and I9, which were the currents of those sources, the voltage sources that were unknown. I8, I9, okay. Then there are knowns or parameters of the problem. And that was R1 through down here R7, but also VS, IS, alpha, and beta. Okay? So a convenient way of doing this is to define a vector of your unknowns. In this manner, where you put all your unknowns, V1, V2, V3, V4, V5, V6, V7, I8, and I9. And here you have a matrix. So in this case, this is going to be a 9 by 9 matrix. So this is your vector of unknowns. This is a 9 by 9 matrix. And so this matrix multiplying this vector means that each row of the matrix multiplies the column of the vector and gives you the left-hand side of one of these equations. So for instance, for the first one, the first element will be 1 over R1 plus 1 over R2. Because that multiplies V1. And then the second element would be minus 1 over R2. And then the third element would be minus 1 over R1. And notice that this equation has only V1, V2, and V3 in it. So all the other factors here have to be 0. The factors that multiply V4, V5, V6, V7, I8, and I9. So 0. So basically you have one element here, another here, another here, and 6 zeros here. And similarly for all the other equations. So you would have 9 lines here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And as you can see, these the elements of these rows and columns of this matrix, many of them will be 0 because each equation only has a few of the variables in it. So this will be a relatively sparse matrix. And then all the other elements, they will be things in terms of the resistances, as well as if you look at the equations, here there is also alpha and beta. The elements are in terms of the resistances and alpha and beta. And then you have to take care of the right hand side of the equation, and so this will be another vector on the right hand side. And as you can see, for instance, the first equation, second equation, and third equation that we have explicitly written here, they all have 0 on the right hand side. But then if you write all the other equations that I ask you to complete on your own, which are really these that you will simplify, you will see that some of them have the sources I sub s and v sub s. Okay, and these are actually what make it so that the variables in the circuit are not all 0, because if you had no source, there would be no voltage or current anyway, or everything would be 0. So ultimately, the right hand side of the equation, which is this vector with 9 rows also, will have a bunch of zeros, but some non-zero elements that depend on the sources. So this is, you might say, the vector of sources. So its non-zero elements are due to the independent sources. Okay. Again, this is something that I'm asking you to complete on your own by simplifying these equations. And so consider this basically like a homework type of thing. It's very good practice. Okay. But this is it. Once you have this, if you take a computer program, for instance, you can do this in MATLAB very easily because you have the matrix of coefficients and multiplying a vector of unknowns, and you have on the other side a vector of knowns, and you can very easily get all the unknowns from this. Okay, so it's just all the techniques that you've learned in linear algebra, basically. Okay, so this really completes nodal analysis. We will come back and talk a little more about this pattern of what these coefficients in this big matrix are going to be. But that's basically it. So the rest is just practicing in circuit after circuit. Okay. So we will take a brief pause and kind of switch gears and talk about mesh analysis. Okay, so let's talk about mesh analysis. And fortunately, there is a lot of similarities with nodal analysis. In fact, you can think of these two methods as one being the dual of the other. Recall that when we started this discussion of nodal and mesh analysis, I said, well, this is It's not really new physics, it's a way of arranging your equations. So if you have written all your KVLs and KCLs and element relationships, if you decide to first solve for the voltages and then using those find other things, you're essentially doing nodal analysis. But if you're doing so with node voltages rather than element voltages. On the other hand, if you're interested in first finding the currents, you're then essentially doing mesh analysis, with the caveat that we define mesh currents rather than element currents. So in nodal analysis, instead of element voltages, we used node voltages. In mesh analysis, instead of element currents, we use mesh currents. Now, what do I mean by mesh currents? So in essence, here we are interested in finding currents. Mesh currents first. Now, what is a mesh current? Again, consider an element connected somewhere. And yeah, the number of connections on the two sides are not necessarily the same, of course. Again, it has element voltage and current. Now, instead of relating the element voltage to node voltages, we are going to take this element current, I, and relate it to the mesh currents. And by mesh currents, what do we mean? Well, a mesh is essentially a loop, but a loop that doesn't have any other branch inside it. So basically a simple loop. So imagine this element being connected to a bunch of other things here. So maybe to something else here, and to something else, and something else. So this is a mesh. A loop that doesn't have any branch in the middle. So you might say it's a simple loop. Because recall, you could have a loop that combines multiple loops, and so for instance, you can go through or around the entire circuit, and that would be a loop, but that would have a lot of things in the middle. A mesh is one of those simple ones. And so you would have perhaps a mesh on this side of the element and another one on this side. And so you define these mesh currents. So let's define this mesh current, capital I1 and capital I2. And these are not the currents of any particular element in general. They are some intermediate objects that help you write the element currents in terms of them. The same way that node voltages were not the voltages across any particular element in general, but you could use node voltages to write the element voltage. So now with mesh currents and currents in general, maybe it's a little more abstract. Sometimes it's a little harder to visualize, so you have to be more imaginative. But basically what we are saying is this. Imagine this element being maybe a two-lane road. And so you have current I1 going through it. And the way I have specified the direction of this current I1 is going, in the element, is going from left to right. So one lane going one way. And then for current I2, it's going from right to left. And so the net current in the element, the net current I, which is the actual element current, is the difference of the two. So in this case, I1, which is going in the same direction as little I, minus I2, which is going in the opposite direction. So imagine you had 10 cars going from left to right per second, and 3 going from right to left per second. So in total, you have a displacement of 7 cars from left to right per second. And that's the actual net current in the element. So in this case, of course, it's not cars, it's charges. Okay, but I1 and I2 themselves are not things that an ammeter would measure. If you add an ammeter to this branch next to this element, it would measure the net current in the element. That's little I. Okay, so I1 and I2 are mathematical objects that we have defined to write the current I in terms of. And then we will see that this helps us simplify the solution of the circuit by writing our equations in terms of these mesh currents. So I1 and I2 are mesh currents they are not the physical current going through the element, but they are mathematical objects that we can write the element current in terms of. And in this case, like I said, the little I, the element current I, is I1, the current of this mesh, minus I2, the current of the other mesh. So big I1 minus big I2. This is really the only concept you need to understand to be able now to turn your KVLs and KCLs into a mesh analysis formalism. Okay, so let's try to see this in practice with a small example. So like we did for nodal analysis last time, here we'll start with a simple example for mesh analysis to see how these things play out. Okay, so example. So consider this circuit. No emphasis on the actual numbers themselves, but so it's kind of like the example we did last time, maybe 3 ohms here, 6 ohms here, 2 volts, 4 volts. No emphasis on the numbers themselves, but just to see how this is done in practice. Okay, so if we want to solve this with our KVLs and KCLs, well, this is what we would do. We'd have the element voltages and currents. So let's call this V1, I1, V2, I2, V3, I3, and then you have, of course, the current through the voltage sources. And here, for instance, I1 is also going through the 2 volt source. if you're interested in the current here, you can also define the current for this voltage source. Let's call this I4. Okay. And so basically, you're going to do your KVLs and KCLs. So let's write that down quickly. So if I want to do my KVLs and KCLs, well, I have a KVL here. Minus 2 plus V1 plus V2 equals 0. And I have another one here. Minus V2 plus V3 equals 0. And I have another one here. Minus V3 plus 4 equals 0. And then I have the KCLs, which involve all the nodes. There's a big node here. There is a node here. There is another node here. And so the KCL up here, you might say it's trivial. So if you wanted to nonetheless define a separate current for this voltage source, this KCL is simply minus I1 minus I5 equals 0. And the same way as the fact that, you know, some of our KVLs down here are trivial, but we wrote them nonetheless. So then for the other node, you have I1 minus I2 minus I3 minus I4 equals 0. And finally, the last node, but that's not going to give you a new or independent equation, as we've talked about before. And then the element relationships, V1 is 8 times I1, V2 is 3 times I2, and V3 is 6 times I3. Okay, and that's that. Let's see, how many unknowns do you have? I think 8 unknowns and 8 equations, right? So that's good. Nothing new here. Writing things in terms of mesh currents is what we are going to do next. And for that, I'm going to define these mesh currents. So for each of these 3 meshes, so these loops that are empty in the middle, these very simple loops, I'll define a mesh current. I'll define the mesh current I1, the mesh current I2, and the mesh current I3. Now, one thing I should emphasize here is that the direction of these mesh currents, you know, I'm used to doing things clockwise. But this has nothing to do with the direction in which you have to go around to write your KVL. You can go around clockwise or counterclockwise to write your KVLs, and you can define a mesh current clockwise or counterclockwise. Okay, these are separate concepts. What's important, as always, is to stay consistent within what you're doing, and we'll see examples of that in practice. Okay, so in terms of mesh currents now, what do I have? Well, I have the element currents to relate to mesh currents. That's my next step. So for instance, from the definition, the type of example I gave up here, if I had an element that bordered 2 meshes, its mesh current would be, in this case, I1 minus I2, given the directions that I have assigned to little I and I1 and I2. An example of that would be here for my little I2. In this case, little I2 is I1 minus I2. Little I2 is big I1 minus big I2, given the directions that I've specified. Little I3 is big I2 minus big I3. Okay? So let's write this down now. So element currents in terms of mesh currents. As I just said, little I2 is I1 minus I2. So big I1 minus big I2. Little I3 is big I2 minus big I3. How about little I1? Now I1 is the element current for the 8 ohm resistor, which is actually only part of one mesh number 1. So its current is actually just the mesh current itself. It's like being a one-way street. There is no other mesh current going in another direction in it. So little I1 is simply big I1 in this case. It's just a special case. It's a simpler case of the general case. Recall that I said mesh currents themselves, so the big I1, the big I2, the big I3, are not physical objects. They're not what you measure in general. In a special case like this, however, because the element, the 8 ohm resistor, was only part of one mesh, there's nothing else there. It just so happens that as a special case, its element current is equal to that mesh current. So the mesh current turns out to equal the physical quantity element current. But that's just a special case of something that happened. But in general, mesh currents are, again, as I said, I want to distinguish between that and the physical currents of the elements. So it just happened to be the case that little I1 is the mesh current itself. And you can see there that little I5 is minus the mesh current, the way we have defined the directions. Okay, and finally for little I4, we have it equal to the mesh current I3, again in a similar sense. Okay, so that's it basically. Next is to put these into your KVLs and KCLs and simplify things, and you have all the equations in terms of mesh currents. So let's do that. So place them into the KVL, KCL, and element relationships. So first KVL, minus 2 plus V1 plus V2. But V1 is 8 times little I1. So minus 2 plus V1, which is 8 times little I1. And little I1, in this case, just happened to be the same as big I1. Plus V2, which is 3I2. And I2 happens to be big I1 minus big I2. So that's equals 0. The next KVL, minus V2, which is minus 3I2, I2 being I1 minus I2, big I1 minus big I2, plus V3, which is 6 times little I3, which is big I2 minus I3, equals 0. And finally, minus V3, which is minus 6 little I3, and little I3 is simply big I2 minus big I3, equals 0. not equals 0, but plus 4 equals 0. So these are my KVLs. How about KCLs? Minus I1 minus I5. Okay, so minus little I1, which happens to be the same as big I1, minus I5. So minus little I5, which happens to be minus big I1, equals 0. The next one, little I1, so 1, minus I2, little I2, which is I1 minus I2, minus little I3, which is minus I2 minus I3, minus I4, which is minus big I3, equals 0. These are my KCLs. And element relationships I have already implemented by incorporating Ohm's law into my KVLs. Okay? Well, now let's see what we see. So simplify things now. So first equation, I have, for I1, I have 8 plus 3. So if I simplify further, I get 11 I1 minus 3 I2 equals 2. Please verify that I've done things correctly. The second KVL is minus 3 I1 plus 9 I2 minus 6 I3 and equals 0. And the third KVL is minus 6 I2 plus 6 I3 equals minus 4. So these are my KVLs. How about KCLs? Well, the first one is minus I1 plus I1 equals 0. So 0 equals 0. The second one is I1 minus I1 plus I2 minus I2 plus I3 minus I3 equals 0. So another 0 equals 0. This is, again, remember, KVLs. And this is KCLs. Also, what happened? KCLs became trivial equations. Now think about it for a moment. Does this mean that there is really no information in KCL? I mean, this is something we've been using and gotten real information from it for the past month or so. So what kind of trick is this? Think about that for a moment. What happened? Okay, let's see together. You remember how in nodal analysis, when we wrote things in terms of node voltages, KVLs became trivial. That wasn't because KVLs were not something real and important. It was because the way we had defined node voltages and their relationship with element voltages, basically we had implied KVL. So they were automatically incorporated. A similar situation is happening for KCLs here. So KCLs, by virtue of the way that we have defined the mesh currents and their relationship with the element currents, KCLs are automatically taken care of. The fact is, by working with mesh currents, KCLs are automatically implied. Okay, That's all that happened. And so you don't need to write them explicitly. And so if you look at the system of equations we came up with, that's 3 equations, 3 unknowns. Those are the mesh currents, and relatively simple to solve. Now, of course, you can come up with a bigger example where you have not only, like we had here, some independent voltage sources, but you could also have independent current sources. You could also have dependent voltage or current sources. And so you would have to deal with that in very much the same manner as we did in the big nodal analysis example we just solved. And we will do examples of that next time. But the essence is this. And of course, then you can arrange these in a systematic way in a matrix form, and so on. But this is really the core in terms of the general approach to mesh analysis. This is what it is. So I think this is a good time to stop now. And again, please work on some of the examples that we've given in the assignments. And so this is it for today. Thank you.